Okay, so yeah, so my talk is about some different measures of local periodicity and some what that implies for the global periodicity of an infinite word. So the idea is we would like to measure, the local periodicity at some position I of an infinite word. And we have several reasonable choices for how you might measure what the local periodicity at a given position of a word might be. For example, you might consider, repetitions in the word that begin at the position I, repetitions that end at the position I, or repetitions centered at position I. And we're going to look at sort of options 2 and 3 because those are the ones that give us some, that give us the most interesting results. So first of all, what kinds of repetitions are we talking about? So mostly we are going to be looking at squares and cubes. So a square is just the same word repeated twice. A cube is the same word repeated 3 times. And in general, we could define the exponent of a word as the length of the word divided by its minimal period. Right, so a square is a 2 power, a cube is a 3 power, but we could have in general words with fractional exponents and so on. Okay, so let's start with by considering repetitions ending at a given position I. So if we let phi denote the golden ratio, Jeff Shalit had this conjecture that any infinite word with the property that eventually there is a repetition of exponent at least phi squared ending at every sufficiently large position. So he conjectured that if a word with this property was necessarily ultimately periodic, right? So having these every position be the ending point of a repetition with large exponent, large in this case being greater than or equal to phi squared, that this would force the entire word to be ultimately periodic. And this was proved to be true by Gnozzi, Restivo, and Salemi. So here is their theorem that an infinite word is ultimately periodic if and only if every sufficiently large position ends in a repetition of exponent at least phi squared. And the phi squared in the theorem is optimal. It can't be replaced by a smaller number. And the example that shows the optimality of this constant phi squared is the Fibonacci word, right? So Fibonacci word is aperiodic and has repetitions, for exponents arbitrarily close to phi squared. It has sort of every position ending in these kinds of repetitions, but it is not periodic. So phi squared is the optimal exponent in that theorem. So for sort of simplicity, let's consider cubes instead of phi squared powers. So the theorem implies that any word that has all sufficiently large positions ending with cubes must be ultimately periodic. And since the Fibonacci word is not periodic, there must be infinitely many positions in the Fibonacci word that do not end in a cube. So we can ask ourselves, well, can we characterize those positions, right? The positions in Fibonacci where no cube ends. So let's define a characteristic sequence or characteristic function for this property, right? So the property of having a cube end at position n. So let cubes be the characteristic sequence of this property. And so to get, so we're going to get a characterization of this function, but to do it, we are going to have to make use of the Fibonacci numeration system. So we're going to write our positions n in the Fibonacci base, right? This is the positional numeration system with place values given by the Fibonacci numbers. And we forbid consecutive ones in the canonical representation of n in this numeration system. So we'll denote this by this n sub f. Okay, so here is my claimed characterization of the positions in Fibonacci where that end in a cube, right? So for one thing, there are most positions of Fibonacci. Oops, excuse me, let me back up. So most positions of the Fibonacci word do end in cubes. So there are these very long runs of ones in this characteristic sequence cubes sub f. And we can describe the runs in this way. So the run starts at some position I that has this sort of somewhat complicated looking base Fibonacci representation. And then the length of these runs is given by either the 2n plus second Fibonacci number minus 1 or f2n plus 3 minus 1, depending on what this last sort of trailing set of digits denoted by w here. Right, so it looks a bit technical, but the point is we have a description for the starting positions of every run of ones in this characteristic sequence, and we can also describe the lengths of these runs. Now, the runs of zeros, right? So the zeros denote positions in Fibonacci where no cube ends. So the runs of zeros are very short, right? So there are only very short runs of sort of consecutive positions where there are no cubes ending in the Fibonacci word. And basically these runs of zeros have length 1, 2, 3, 7, or 8. And that's basically it. There's an initial run of zeros of length 13 at the beginning, but that's just because it's the beginning. Otherwise, in terms of runs of zeros that occur infinitely often, these have only these specific lengths, 1, 2, 3, 7, and 8. So the longest run of zeros is 8. So there, at most, there are 8 consecutive positions in the Fibonacci word that do not end in a cube. Okay, so how did I actually get this characterization? Well, of course, I used the program Walnut, right? So this is some software that was initially developed by Jeff Shalet's student, Hamoun Mousavi. And the way it works is like this. So the sort of input to the program is a finite automaton that computes my sequence by either reading its input in some integer base k, or Fibonacci base, and it supports some other numeration systems as well. And this automaton reads the input in this numeration system and outputs the nth term of a sequence. So given the automaton defining the sequence S, and then some formula phi in first order logic that involves sort of variables, constants, quantifiers, the usual logical operations, the order operation, addition and subtraction, and indexing into the sequence S. As well as we can sort of multiply variables by a constant, but we are not allowed to multiply two variables in these formulas. So given such a formula and an automaton for S, if the formula phi has no free variables, then Walnut will either output true or false, right? It will say the formula phi is either true or false. If the formula does have free variables, then what Walnut will produce instead is an automaton that accepts the base K or base Fibonacci representations of the values of the free variables that satisfy the formula phi. So, for example, if I want to obtain the ending positions of cubes in the Fibonacci word f, I can do so with this formula, right? So the variables here, I denotes the starting position of the cube, n denotes the length of the period. So this form, and j, the free variable j, denotes the ending position of the cube, right? So this says that there is a cube starting at position I of length 3n, ending at position j, and then the last sort of part of the formula just verifies the periodicity, right? So that indeed this is a cube starting at position I, has length 3n, ends at position j. J is the free variable. So this formula is satisfied whenever j is the ending position of a cube in the Fibonacci word f. And if I translate this into the language of Walnut, so it's fairly easy to translate. Basically, starting after this MSD fib, which just says that we're using the Fibonacci numeration system. After that, the formula can be translated very straightforwardly. So E denotes the existential quantifier, A denotes the universal quantifier, and so on. So it's not hard to see how to convert the logical formula on the previous slide to this version that Walnut understands. And if you input this into Walnut, it will produce an automaton that accepts the Fibonacci base representations of all positions j, where a cube ends in the Fibonacci word. And here it is. Here's the automaton. Right, so this is the automaton that accepts base Fibonacci representations of all positions j, where a cube ends in the Fibonacci word. And so I can use that then to obtain a characterization of the runs of ones, for example, in this characteristic sequence, cubes sub f. Right, so again, I have a Walnut command that characterizes the runs of ones in that sequence, cubes sub f. Right, so it accepts pairs I and L, such that I is the starting position of a run of ones and L is the length of the run. Right, you can, I think, see this from the formula, right? It just sort of verifies that There are n consecutive positions in a row that satisfy fib end cubes sort of equals true, and that that then fails at the next position to the right and the previous position to the left. So this gives me a formula that that gives me these pairs I sub L runs of one starting at position I and having length L. And so if I give this to Walnut, it produces the automaton you see here. Right, you'll see now that the alphabet consists of pairs of digits. That's because there were two free variables in my formula, I and L. So when I read an input in this automaton, the first component spells out the digits of the first variable I, and the second component spells out the digits of the second variable L in the base Fibonacci. So if you sort of study this automaton, you can write down the regular language that corresponds to the I's that are accepted by this automaton. So you can see it written here as a sort of regular language. And you can also see from the automaton that the Fibonacci representation of L is essentially just some alternating sequence of ones and zeros of length determined by the length of this suffix W. Right? So depending on the length of that, depending on the length of that suffix W, whether it's even or odd, we get the Fibonacci representation of L, and we can calculate what that number is. It turns out to be given by these formulas. L is either f sub 2n plus 2 minus 1, or L is f sub 2n plus 3 minus 1. Right, so we get these run lengths L of the lengths of the runs of ones in the sequence cubes sub f. And we could do the same thing for the runs of zeros, right? The positions where there are no cubes ending. We get this automaton, which looks more complicated, but is actually a lot simpler. Because, so this automaton, right, again, it gives me the pairs, I, L. I is the starting position of the run of zeros, L is the length of the run of zeros. And if I only want the lengths, the lengths of runs that appear, what I would like to do then is project onto the second component, right, which is the component that that tells me the lengths. So I project this automaton on the second component, essentially simply by throwing in a quantifier, so an exists I on the first component. Right, so that will essentially get rid of the first component and project the automaton onto the second component, giving me the lengths of the runs. And now I get a very simple automaton, right? And you can see very easily that the lengths accepted by this automaton are, for example, 1 in Fibonacci, which is 1, 1, 0, which is 2, 1, 0, 0, which is 3, 1, 0, 0, 0, 0, 0, which is 8, etc. So we get these run lengths from this automaton, right? So the runs of zeros have lengths 1, 2, 3, 7, 8, and 13. It's not hard to check that 13 only appears at the beginning, but all the other run lengths appear infinitely often in this characteristic sequence cubes sub f. So infinitely often, there are these runs of 8 consecutive positions in Fibonacci where there were no cubes end. And it turns out that the runs of lengths 7 and 8 have their starting positions are fairly easy to describe. So again, you can easily write a walnut command to do this. So I've shown them here because they have a fairly nice description in base Fibonacci. So we know exactly where the runs of length 8 occur in this sequence. But I have no explanation, right? I don't have any theoretical explanation for why there is a run of 8 positions where no cubes end starting there, right? I just know it's true. So like I said, most positions in the Fibonacci sequence do end in a cube, right? So the density of the zeros in this characteristic sequence is 0. And you can determine this by computing the automaton for the positions where there are no cubes ending, right? You can see the automaton here. And to show that this has density 0, it's enough to show that this automaton only accepts polynomially many strings of length n. And this can be done easily by looking at the structure of the automaton, right? So an automaton will accept exponentially many strings, sort of if and only if there are 2 cycles in the automaton that can both reach each other. And you can see in this automaton, well, there are some cycles, but no 2 of them can reach each other, can mutually reach each other. All right, so once you leave a cycle, you can never return to it. So this automaton only accepts polynomially many strings of length n. So we get that the density of zeros in this sequence is 0. All right, so that's that's sort of the list of results that that I was able to get for the Fibonacci word using Walnut. So it would be a natural enough question to see if the same kinds of things could be calculated for other Stermian sequences. For example, you know, the characteristic Stermian sequences with slope alpha. So you could define the same kind of characteristic sequence, cube sub w, for any infinite word w, that is the characteristic function of the positions that are the ending positions of a cube. And you could then try to compute what is the longest length of a run of zeros in this sequence that occurs infinitely often. Right, so for Fibonacci, it was 8, right? The longest run of zeros that occurs infinitely often was 8. So, like I said, I have no theoretical explanation for that, right? I just I can get the answer using Walnut, but I don't know why that is true. So you could ask yourself, well, why? Is there some explanation for that? So is that that length 8 somehow determined by the continued fraction expansion of the slope alpha? What's the greatest or smallest possible values for this maximum length run of zeros over all characteristic Stermian words? Right, so for Fibonacci, it's 8, but there are other Stermian words that have that do not have runs of zeros of length 8. So what are the possibilities, right? So there are a couple of open problems related to these Stermian words. Okay, so now let me, after sort of mentioning those open problems, let me switch now from considering repetitions ending at a position I to repetitions centered at a position I. Right, so you can sort of ask yourself the same kinds of questions about, but now you consider repetitions centered at a position I. And so there's a similar theorem, right? So we had this theorem of Mignosi, Restivo, and Salemi that said that if an infinite word has repetitions of exponents at least phi squared, eventually appearing at every position, then the word is ultimately periodic. So the analogous result for repetitions centered at each position is that if an infinite word eventually has a square centered at every position, then the word is ultimately periodic. Right. So this was shown by Duval, Mignosi, and Restivo. So this is the analogous version of the theorem for repetitions centered eventually at every position. And once again, the Fibonacci word was optimal for this theorem, just like it was for the previous theorem. And indeed, the Fibonacci word, since it's not periodic, it cannot have a square centered at all sufficiently large positions. So there must be infinitely many positions in Fibonacci where a square is not centered. But it turns out that there's a very simple description for those positions. So almost every position in Fibonacci is the center of a square, except those positions j equal to the nth Fibonacci number minus 2. So they've already characterized these positions, the positions in Fibonacci where there either is or is not a square center. And it's a much simpler description than my description of the positions where there are cubes ending. Right, that was a very complicated thing involving these automata, but this is a very sort of nice, simple description. So this definition of a square centered at a position I is a sort of well-studied measure of the local periodicity of an infinite word at a position I. And this can be sort of analyzed in terms of this so-called periodicity function. So let's define a periodicity function, P sub W, as a function of the position I, and it is the length of the shortest square centered at position I. And if there is not a square centered at position I, then what you do is there's this sort of extra part of the definition here. So if there isn't a square centered at position I, then you basically imagine extending the word to the left until you get a square centered at position I, and then the shortest such square is the value of the periodicity function. Right, so this is always defined if your word is recurrent, and we will only be considering recurrent words. So we have this periodicity function that measures the local period in terms of the shortest length of a square centered at that position. Now, this periodicity function, though, can fluctuate wildly, right? There can be a very short square centered at position I, but then nothing sort of centered at position I plus 1. So there can be a huge jump in the value of the periodicity function going from position I to position I plus 1. So it's not a very good complexity function as a complexity measure for an infinite word. So Mignosi and Restivo defined a periodic complexity function by simply taking the average of the periodicity function over its first n values. All right. And so I should also apologize. In the abstract that was sent out, I, for some reason, just wrote the wrong names when attributing this periodicity complexity function. The correct reference is indeed Mignosi and Restivo. So Antonio corrected me this morning. I don't know why I wrote the wrong names in the abstract, but this is due to Mignosi and Restivo. So we have this periodic complexity function is the average of the local periods over the first n positions, right? So big P is the sum of the complexity function, or the sort of first partial sums, and little h is the average, right? So little h is the function we are going to look at. So the average of the local periods over the initial positions. So in their paper, they studied this function little h, right? This average of the local periods for the Fibonacci word and the 2A Morse word. And they found that the 2A Morse word had its periodic complexity function was order n, right? So the average of the local periods was sort of big theta of n. But for the Fibonacci word, the average of the local periods was big theta of log n. So significantly smaller. Right, so basically there are, in the Fibonacci word, at most positions, you can find a short square centered there. But for 2A Morse, you can very often find a short square, but then there'll be positions where you can't find a short square centered at that position. And you can see this by looking at some initial values of the local period function, right? So you can see in the table, right? So there are some small values, 1, 2, 1, 1s and 2s appear quite often. So there'll be a very short square of period 1 or 2 appearing quite often, but then there's a big jump, right? Like these values, like 24, for example, means that there is no square in 2A Morse centered at, for example, position 9. Right, so the value of the local period function has these big jumps. So once again, I can obtain a precise characterization of this local period function using Walnut. And in fact, the commands to do this appear in the manuscript of Jeff Shalet's Walnut book that is coming out sometime. So you can already find this in there. So these are the Walnut commands that will compute that local period function. So the first command just checks if two factors at positions I and k of length n are equal. The second command verifies the local period condition, right? Either there's a square centered at position I, or you have to extend the word to the left until you get a square centered at position I. And then the last command actually computes the values of the periodicity function. So it's the least, sort of the least length that satisfies the previous formula. So if I put all of these things into Walnut, it will give me an automaton that will compute exactly the function little p, the local period function for the 2A Morse word, right? So it'll accept pairs I and P of I. And that's the automaton, right? So of course, this is operating in base 2, since this is the 2A Morse word. And it's a fairly simple automaton, so you can actually sort of study this and figure out more or less exactly what is going on. And if you study the automaton for a little bit, you will find that for even positions, the local period is either 1 or 2. Right, so there are lots of these 1s and 2s. And then for odd positions, you could get these sort of larger jumps in the local period. It's going to be 3 times the power of 2, where 2 to the t is, I guess, the largest power of 2 smaller than I. Right, so we can get an exact sort of just a relatively exact description of this local period function. Given that, it's pretty easy to estimate the average. Right, so first of all, the partial sums. We can estimate the partial sums and get this kind of thing. So bounded above and below by some quadratic in n, and from that we can easily get the average. So let's look at that partial sum. Of course, we can split the sum of the local periods into the even and odd terms. The even terms have value 1 or 2, right? So if we sum over the even positions, this is going to be between n over 2 and n, pretty much. If we sum the odd positions, well, if you look at the formula for the odd positions, basically this is going to be between 3i and 3i over 2. So we can again easily find upper and lower bounds. Right, in the first case, pi is at most 3i. In the second case, pi is at least 3i over 2. So we can sum these over odd values of I and get some estimates for the sums at the odd positions. Add the odd and even positions, and you get the estimates that you see at the bottom of the slide. Divide by n, and you get the average. Right. So this is essentially. So this is just a version of what Mignosi and Restivo were able to get, but with some slightly better constants. Right, so in particular, the average of the local periods is big theta of n for the 2A Morse word. And we were able to do this because the automaton for the local period function was pretty simple. But if you choose some other sequence, right, other than 2A Morse word, this might not be the case. So there are other ways to analyze the asymptotics of these local period functions. So one method is to obtain a linear representation for this function. So this is once again something that that Walnut can do. So what do I mean by a linear representation, right? So I mean, if you are familiar with the theory of k-regular sequences, then you know what this is, right? Basically, we have a row vector v, a column vector w, a pair of matrices associated with the digits 0 and 1, such that P of I can be computed by writing V times this matrix product times W, where the indices of this matrix product come from the binary expansion of I. right? So you write down I in binary and then take the corresponding product of these integer matrices and do this multiplication, and the result should give you the value of P of I. Right, so luckily for us, Walnut can actually produce the linear representation. Here's the command that does it, right? So I want a linear representation for this function Tm local period I comma n. So n is the value of the function that I want, right? Basically, I just want n. But I have to do something slightly artificial because Walnut will not give me the linear representation for n. What it does is it gives me the linear representation for the number of values of the free variable that makes the formula true. So I have to kind of artificially add a free variable m such that the number of m's that satisfy this formula is in fact n. And then it will give me the linear representation for n. So anyways, it's a little bit of an artificial thing I have to do, but this command will give me a linear representation in terms of I of the function P of I for the 2A Morse word. That is the point, and here it is. So, all right, so there's my V, there's my W, there are my two integer matrices for my linear function. Right, so Maple can produce this with a, and it gives this to me as a Maple worksheet. So I'm going to use this for the period doubling sequence, right, to get to analyze the periodic complexity function of the period doubling sequence. So the period doubling sequence is a sequence closely related to the 2A Morse word. It's obtained by iterating the substitution 0 goes to 0, 1, 1 goes to 0, 0. It is also 2 automatic. So we can apply Walnut in the same way as we did for 2A Morse. If you actually show a table of the local periods for period doubling, you'll see that actually the local periods are quite small. And in fact, you would conjecture that the average local period grows like log n. In other words, like the Fibonacci word, which also had its average local period growing like log n, right? So period doubling, in this case, its periodic complexity behaves like Fibonacci, rather than the 2A Morse word. So it has lots of these short local periods. So we can calculate this from the linear representation. So I do what I did before for 2A Morse using Walnut. I get the automaton for the local periods. I use Walnut to get the linear representation for the local periods. And using that, I can get the following estimates for the partial sum and the average. Right, and you'll see that the average local period is essentially between 1/3 log n and 4/3 log n. So here's how I do the estimate this time. So I'm going to evaluate the partial sums up to these powers of 2 to the L, right? So I take the partial sums of the local period function. Because I have a linear representation, so I replace P of I with my linear representation. And then I notice that this sum over all possible matrix products is simply what I would get from the binomial expansion of M0 plus M1 to the L. So I define a matrix M as M0 plus M1. And so this partial sum simply reduces to V times M to the L W. So basically, this is now just simply a linear recurrence sequence that I can solve using the usual techniques for solving linear recurrences. Right, so I calculate a minimal polynomial, I find roots, I get this, this expression here, sort of polynomials times powers of the roots, and all I have to do is find the constants. Right, so I do the usual thing. I use the initial values of the sequence to find solve a linear system, find the constants, and I get this expression here for the partial sums at powers of 2, which I can get upper and lower bounds for, and now I simply substitute. So if n is between these powers of 2, then log n is between L and L plus 1. After doing a little bit of calculation, I can get upper and lower bounds for the partial sums. Divide by n, I get these upper and lower bounds for the average local period, right, between 1/3 log n and 4/3 log n. All right, so this time I was able to get my sort of estimates using this linear representation and doing a little bit of calculation, right, solving this linear recurrence, etc. There's yet another option if I want to find asymptotics of for these local period functions. If I have a linear representation, I can also use the techniques of Philippe Dumas or Heuberger and Kren. So if you have been regularly attending the numeration seminar, then you've seen a couple talks describing these techniques. So Kren gave a talk there about these methods, and so did Michael Kuhns, right, just very recently in the last couple of weeks. So you would have seen this in the numeration seminar. So for example, we could apply that to the Root and Shapiro sequence, right? So Root and Shapiro, again, a 2-automatic sequence. We can do the whole process. We can get a linear representation using Walnut. In this case, the matrices are quite large. They are 31 by 31 matrices. But using the techniques of Dumas or Heuberger-Kren, we can rather easily get a formula for the asymptotics that, you know, so the partial sums grows like n squared times this sort of periodic sort of modulation thing, which you would have seen again if you in the numeration seminar talks. So using their sort of techniques, you can also get these kinds of asymptotics from the linear representation. So this is what we get for Root and Shapiro. So the average local period for Root and Shapiro is essentially linear, but then times this sort of strange fluctuation given by the function phi. So that is it. Walnut. Here's a link to Walnut, and that's the end. Thank you very much. Oh, Jeff, you're muted.
Sorry. Thank you, Narad. Are there any questions? You can either unmute yourself, like I failed to do just now, or type them into the chat. I see Christoph has a question.
Yes. Do you hear me?
Yes.
Yes.
Yes. I just wanted to know if Walnut can compute the minimal representation of the matrix representation.
I think that is not currently built into Walnut. I mean, I think Jeff knows how to do it, but I think he has a separate program to do it, right?
Yeah, currently it's not part of Walnut, but I have some Maple code that was written by a student, which I'm happy to send to you if it has any value to you.
Okay, thank you.
Are there other questions? So I have a remark, but the remark is, at least in theory, this question about the runs of zeros for all Stermian words in looking for where the cubes end. That's something you could program in Pecan, and so almost certainly the answer is no. That this bound of upper and lower bounds that you had, 8 and what was it?
3.
3. So the upper bound of 8 is almost certainly not true. But you could even Pecan, you could say, well, what are the partial quotients for which it's true? And in theory, Pecan would describe them. So you might try that.
Right. Yes.
For the minimum one being 3, I think that's quite likely, and maybe Pecan could even prove that.
Mm-hmm.
Yeah.
Right. I have definitely been meaning to learn to really learn Pecan.
Yeah. So have I, but I haven't done it. Oh, actually, no, I don't think it's 3. I think I found a counterexample, but at least in theory, it could be proven. No, maybe my counterexample's wrong. Okay. Well, you and I should both download Pecan and try to figure out more about it. So
right.
Yeah.